Hello everyone. In this example, we are asked to find all the zeros of the polynomial function f of x, which is defined as x cubed plus 7x squared plus 11x minus 3. All right, so if we want to find all the zeros of our polynomial function, the first set of zeros that we'd look for are those rational zeros. So we can use our rational zero theorem or our rational roots theorem to help us construct the possible rational zeros of our polynomial function. And that first step of that process comes down to identifying the constant and leading coefficients of your polynomial in that expanded form. So the constant term of our polynomial, since it's already in its expanded form, is -3, and the leading coefficient is +1. And so next we need the factors of our constant at the end of our polynomial and the factors of our leading coefficient. And so our factors for -3 are going to be ±1 and ±3. And our factorization for +1, well, it's pretty boring. It's just +1 and -1, right? We can do -1 times -1 to also create a +1. So remember, these factors that make up the constant term at the end of our polynomial are the potential numerators of our rational zeros, and these factors that make up the leading coefficient of our polynomial are the potential denominators of our rational zeros. So in the numerators, we're going to have either ±1 or ±3, and in the denominators, we're always just going to have ±1. That's kind of the nicest case to have here when you have a leading coefficient of 1, because you're really just focusing on the factors of the constant term then. So our possible zeros are ±1 divided by ±1, or ±3, again, divided by that ±1, but division by 1 is not really changing anything here. All right, so we have 4 potential zeros. We have a cubic function though, so we know we have at most 3 zeros. So now we have to figure out which of these 4 numbers actually represents a 0. So we can do that quickly by plugging these numbers into our function and seeing if we actually get an output of 0. All right, so if I evaluate my function at x equals 1, I get an output of 16. That's no good. If I evaluate my function at the input of -1, I get the output of -8. Also not what we're looking for. If we plug in x equals 3, we get 120. It's got a 0, but it's also got that 1 and 2 in front, so that's no good. If we plug in x equals -3, we finally get what we're looking for, a 0 of our polynomial. So now we have to remember that this 0 is always going to correspond to a factor. Right? So we know that x equals -3 is a 0. And that implies that x plus 3 is a factor of our polynomial. Right? Because what x value makes this factor become a factor of 0, which multiplies everything by 0 and zeroes out the whole thing, only when x is equal to -3. That factor is always going to look a little bit opposite of the actual x value that corresponds to the 0. So we know that our 0 at x equals -3 is going to correspond to a factor in our polynomial of the quantity x plus 3. And now to see how the rest of our polynomial is going to factor out, or how we can rewrite it in a semi-factored form, we need to do some polynomial long division and actually divide out that known factor of x plus 3 from our polynomial. All right, so remember when we were performing this polynomial long division, we're really just kind of focusing on the leading terms for each piece at each individual step. And so for our first step, we're really kind of answering the question of x cubed divided by x. How many times does x go into x cubed? Although I think an easier way to digest that, a better way to phrase it, is to ask the equivalent question of what do we have to multiply x by to get x cubed? Well, that's going to be an x squared. So our next step is to actually multiply our entire divisor by that first piece of our quotient, that x squared, and that'll give us x squared times x is our x cubed, then x squared times 3 gives us 3x squared. Now this is just like the rest of our long division process with integers or numbers. So now we subtract away from the original quantity we are dividing, that first product from our divisor and our quotient. So next we're going to subtract away from x cubed plus 7x squared plus 11x minus 3, that first product we get from x plus 3 and x squared. So those x plus 3's are going to cancel out. That first piece should always be canceling out in this process, otherwise we made a mistake somewhere. So then we have 7x squared minus 3x squared. That'll leave us with 4x squared left over. So that'll leave us with 4x squared left over, but then we have to also remember to bring down the rest of the pieces, that 11x and that negative 3. And so we're done with the first step or iteration, but now we do it again. This time we focus on the question of how many times does x go into 4x squared, or what do we have to multiply x by to get 4x squared? And that should be just a 4x. So next step, just like before, we perform that multiplication. X times 4x gives us the 4x squared, but then we have to also do 3 times 4x, which gives us a 12x. So we subtract this new product away from our dividend to create our new dividend. The 4x squareds cancel out. We have 11x minus 12x, which gives us negative x. Bring down the negative 3. And so now we have one last iteration to go. How many times does x plus 3 go into negative x minus 3? And again, we can just focus on the first pieces or rephrase it. What do we have to multiply x by to get negative x? And that's negative 1. And so now just to finish it off, it should be very satisfying. Negative 1 times x plus 3 gives us negative x minus 3. Now we're subtracting away, and there's a couple double negatives going on here. Everything cancels out, leaving us a remainder of 0, which is what we should always have happen if the factor we are dividing our polynomial by actually corresponds to a 0 of our polynomial. And so remember, the whole point of doing that polynomial long division was to allow us to rewrite our function, our polynomial, in a slightly or more factored form. We know one of our factors is going to be x plus 3, and the quotient, or the answer that we get out of our polynomial long division with a remainder of 0, is going to be the other factor for our polynomial in this partially factored form. And so that's going to be the quadratic x squared plus 4x minus 1. So now if we want to find all the zeros of our polynomial, which is equivalent to this one right here, we already know 1 is negative 3. To find the remaining zeros, we just now need to work with this factor of x squared plus 4x minus 1. And so we could try to factor that, or maybe try the rational roots theorem again on just this smaller quadratic piece, but that's really going to be kind of a waste of time, because if it had a rational 0, we would have found it the first time around when we were looking for the rational zeros of our original function. It doesn't quite work out that way always for zeros of higher multiplicity. So what I mean by that is if x equals negative 3 was a 0 of multiplicity 2, if we divide our polynomial once by x plus 3, then we're only going to pull off one of those factors of x plus 3 from our polynomial, meaning the second factor of x plus 3 may still be in there. But just in general, if we're going to try to solve our polynomial function almost like from scratch, but from this partially factored form, we would need to set that first factor of x plus 3 equal to 0, or the second factor of x squared plus 4x minus 1 equal to 0. We already know what happens for that first factor. It gives us the solution that we got from the rational 0 theorem, x equals negative 3. But now we need to solve this quadratic equation to find the remaining solutions. And I mentioned before, we could try to factor this, but we would have no luck. So in order to solve this quadratic equation, we're going to have to use our quadratic formula. Right? X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So let's see. Our b value is positive 4, so negative b will be negative 4. Our b squared value is 4 squared, or 16. We have to subtract away from that 4 times our a value of 1, right? That's like a 1x squared, even though we don't write that factor of 1. Then we have to multiply that by our c value of negative 1 and divide everything by 2 times our a value of 1, or just 2. All right, so let's go ahead and simplify our radicand, or that number underneath our square root. We got a product of 2 negatives here, making this a positive 4 that we are adding to our 16. So that'll give us a total of 20. So x could also be equal to negative 4 plus or minus the square root of 20 all over 2. Or we could simplify that, and we should. Right, we can break apart the square root of 20 as the square root of 4 times the square root of 5. Then the square root of 4 is a perfect square that turns into a factor of 2. So we get negative 4 plus or minus 2 times the square root of 5 all over 2, but everything there is divisible by 2. So we can actually do that division or cancel that factor of 2 out. And we end up with negative 2 plus or minus the square root of 5. So the original question was find all the zeros of this polynomial function that we're calling f of x. And our zeros are x equals negative 3, x equals negative 2 plus the square root of 5, and x equals negative 2 minus the square root of 5. So it took a bit of work, but we were able to successfully find all the zeros for our cubic polynomial. And there's going to be 3 zeros for a cubic polynomial. The number of zeros is always going to match up with the degree of your polynomial if you include repetitions for zeros of higher multiplicity than 1.